Then now we move on to the last presentation in this session for today. It will be given by Yan Xu from the Geological Survey of Shanghai. And the presentation will be on a study on the influence of supertall building load on adjacent tunnel subsidence.
Okay. Thank you, Professor Ezra. Good afternoon, everyone. I'm Yan Xu from Shanghai Institute of Geological Survey. It's my honor to be here to introduce some study on the influence of supertall building load on adjacent tunnel subsidence. And this is also a contribution of the IGCP 63 project of the IUGS and UNESCO. So my presentation will be divided into 3 parts. And first, I will introduce the coupling information of geological stratification and tunnel structure. So as we know, Shanghai has a long history of land subsidence and serious land subsidence. In the past 100 years, the average subsidence in Shanghai is more than 2 meters. So there are 300 to 500 meters thick quaternary sedimentary strata widely distributed on this area. So which is the main internal reason of the land subsidence in Shanghai from the past until now. So for the urban development, there are various of infrastructure have to be. Okay. Okay, thank you very much. Okay, thank you. So there are various infrastructures built at different depths in this subsoil, such as the municipal pipelines, the transport infrastructures, including the metro lines. Nowadays, the underground infrastructure usually built below 40 meters. So I think it will be developed deeper and deeper in the future. So there are 5 confined aquifers in Shanghai below under the ground surface. So the land subsidence characteristics in here will develop with the change of the groundwater level and the process of urban development. So at present, under the premise of controlling land subsidence, so the extraction of the water from the aquifers is already less than 1 million tons a year. And the artificial recharge remains at a stage of 20 million tons a year. So the groundwater keeps rising in here. And as we can see in the figure, by 2020, compared with the historical lowest water level of confined aquifer 5, the water level exceeded over 40 meters in the past years, and it still maintained a recent trend. So the metro tunnel usually built at a depth of 5 to 30 meters in these soil areas. So the additional stress caused by the uneven deformation of the surrounding soil layers can apply direct to the underground tunnels passing through them. So we use multiple methods to monitor the deformation of the soils, such as INSA, the GNSS, and the leveling, as well as the stratification extensometers. So in this study, we analysis mainly based on the data from the extensometers. So this is we selected 2 typical metro lines in Shanghai, and the monitoring work started when the tunnel construction is completed. And line B was built nearly 10 years after line A. We can see that the deformation trend of line A can be directly divided into the post-construction settlement and the long-term deformation stage. So but the post-construction settlement of line B is short. But for both lines, the development of the terminal vertical deformation and the land subsidence trend appeared obvious differences. So why is this? Because the land subsidence characteristics in Shanghai is coincidence in different areas, because some area in Shanghai has already began to rebound. So we also selected line C in the land subsidence zone and line D in the land rebound zone to analysis. And from this picture, we can see that both lines, in both lines, the soil layers above the tunnel appeared a trend of compression, and the compression rate gradually slowed down. But the soil layer under the tunnel appeared a trend of rebound, and the rebound rate is still accelerated. And for both tunnel, the tunnel deformation is coordinated development and controlled by the soil layer deformation under the tunnel structure. So in the second part, I will introduce the influence of supertall building load on the adjacent tunnel subsidence. For the urban needs of function needs of urban, there are usually large numbers of buildings around the tunnel. So the left picture is the 3D underground space and geological model of Shanghai. We can see that there are a lot of tunnels. The tunnels are surrounded by a lot of pier foundations, and the supertall building load can be transferred to the subsoil and the tunnel structure through the pier foundations. So we selected a typical area in Shanghai for this analysis. The buildings B, C, and D are existing buildings with over 300 meters high, and there is a park with no building built north of the tunnel, and the land subsidence monitoring station is located south of this area. So building A is the newly built building with a height of over 500 meters, and the pier foundation of building A is the diameter is 1,000 millimeters and 88 long. It passes through the soft clay and into the silt and sandy layer. So we will use this case to study the tunnel subsidence during the construction of building A. So the left picture is the tunnel deformation at different positions since 2009, when the tunnel construction is completed. We can see that the tunnel deformation in there appeared general rebound, and the cumulative rebound was the minimum at the building A, and the maximum at the position of the park. And the right picture shows the deformation of the entire tunnel section during the construction of building A. We can clearly see the subsidence peak near building A and the rebound peak near the park. So for a tunnel, the structure at each position will be affected by the surrounding tunnel structure. That means a deformation at a certain position of the tunnel will cause the follow-up deformation of the surrounding tunnel structure. So in order to eliminate the influence of the general rebound caused maybe by the groundwater level rise and the soil layer rebound, so we set a reference point, the reference point at the park. There is no building, no high-rise building built, and we can find it is so interesting to find that the relative deformation appeared generally subsidence instead of rebound. Here, it started to so in the right picture, we can also find that the uneven subsidence can be clearly seen in the position of building A. So we successfully separated the influence of high-rise building load on the adjacent internal subsidence by setting reference points at the position of park. So the land subsidence monitoring station is located within 300 meters south of this area. And according to the extensometers monitoring data, we can find that the main compress in this area appeared in the shallow layer, which is from 14.5 to 1.2 meters, the top soil layer. And we can find that the land subsidence rate gradually exceeded the deformation rate of shallow soil layer. Which indicates that the upper load gradually translates to the deeper soil through the pier foundation and had an influence on the deeper soil deformation. So to study the influence of the supertall building load on adjacent internal structures, we should focus on the stress transfer pattern and the deformation of the deeper soils. So the deformation, as we know, the deformation of the internal structure is so complex, so it's hard to describe accurately only from the field monitoring data. So we also did some experiments to simplify the situation, and this part is not included in the 2020 paper submitted. I will make a brief introduce. And first, we conducted 5 groups of centrifugal model tests, and the similarity ratio was 1 to 100. And CMT1 is a standard group, and the internal depth was changed in the CMT2 and CMT3 groups, and the horizontal distance between the internal and the pier structure was changed in the CMT4 and CMT5 groups. So the measuring elements, including the soil pressure sensor, the laser displacement meter, and stringing gauge, as well as the cable displacement meter. And from the preliminary results, we can find that the left picture is the displacement change of the typical measuring point in the CMT1, 2, and 3 test. We can find that with the increase of the internal depth and the absolute deformation of the internal structure increases, and the included angle between the internal displacement and direction and the horizontal plane decreases from the 77 degree to nearly 73 degree. And another group focused on the horizontal the factors of horizontal displacement. So with the increase of the horizontal distance between the internal and the building, and the absolute deformation of the internal structure decreases, which is different from the last group. And the included angle between the internal displacement and the direction and the horizontal plane decreases from maybe 75 degree to 71 degree. And as a supplement to the centrifugal model test, we also did some numerical simulation, finite element numerical simulation, and for some special scenarios, and the maximum internal deformation, real height difference, the maximum bending moment of internal segment of our analysis by changing the depth of the foundation pit, excavation depth, and the relative position of between the pier and the tunnel, like this. And two more typical scenarios considered strata loss was also considered. And the left picture is the cloud image of the foundation deformation and the pier load. After the pier load was applied, we can find that the model displacement field was we should focus that the model displacement field was reset after tunnel excavation, which indicates that the tunnel extraction was the impact of tunnel extraction was ignored in this analysis, and we can find that the deformation of the foundation soil developed from the center of the foundation pit to the periphery. And in the right picture, we also can find the development of the land subsidence section. We can clearly see the land subsidence funnel, the development of the land subsidence funnel. So the last, I will make some conclusions. First, the present regional land subsidence in Shanghai area was the result of the superposition effect of the shallow soil layer compaction and deep soil layer rebound. The second, with the change of the geological environment conditions, the sensitivity of the internal disturbance to the deep soil layer deformation was higher than the ground displacement. So the third, the internal displacement was coordinated, developed with the underlying soil deformation, and the stress transfer pattern was the key to evaluate the influence of high-rise building load on adjacent internal structures. So the fourth, the factors affecting underground infrastructures are more complex, so the next step in this study required more single-factor analysis by other methods. That's all. Thank you. Thank you for your attention.
Thank you very much for this interesting presentation. So are there any questions for Jan? If not, I have two. So you've showed the modeling that you did for building A and how that affected the tunnel deformation.
Yes.
But in the beginning you showed that there were multiple buildings that were built, but I don't know if they were built at the same time or if there's time in between. But I was wondering, did you also look into the combined effect of the construction pits that had to be constructed for building these building foundations? So have you, or will that be the next step?
Yes, I think it's valuable and the key points of this study, because the factors affecting the internal structure is so complex. So we try to separate the single factors affecting it. And in this case, and the building A was built nearly 10 years after the building B, C, and D. So I think it's had at a center at a certain. I think we can't completely remove the factor affecting by B, C, and D, but I think because we set our reference points at the park, this area also affected by the other buildings. So we set the reference points. We try to eliminate the influence of the other building influence, or as well as the influence of the geological environment change, such as the groundwater level rising. Okay.
Yeah, so this can be purely attributed to the groundwater level lowering because of the construction pit, or is part of the deformation maybe also caused by groundwater extraction in the neighborhood?
Yes,
Okay.
yes, we can see that in the first, it's the absolute attitude. We can see that in this area, the turnout appeared generally rebound. But when we set a reference point, we see the relative deformation appeared subsidence. Yes.
Okay.
We know in this area, the generally land and the soil layer started to rebound, but the tunnel, we see that the relative deformation is subsidence. Yes, it may be caused by the adjacent supertall building load. Yes.
Okay. Maybe questions now? If not, then I would like to thank you again.
Thank you, Emma.